Okay, thank you. Well, I'd like to welcome back everybody for this lecture number 3. Just reposition my screen here before we get started. There we go. And today, of course, we're shifting on to lecture 3, and this is going to focus on these so-called modern concepts of hill slope runoff generation. The last lecture will be November 9th, and that will look at Hillslope hydrology outside of rain events. But tonight we're going to focus on rainfall or snowmelt events and how water moves through our landscapes, particularly at the hill slope scale. Don't forget that our 3 main concerns or questions relate to the runoff source, the runoff flow path, and the runoff travel time. And the latter one, the travel time, is what we'll talk about next class. So this is the topic for today. And we have 4 main sections. We'll talk about what I'm calling hill slope fill and spill, kind of a way that I think runoff is generated that is common across many areas, particularly for subsurface storm flow. Then we'll revisit what are some of the similarities and differences between overland flow and subsurface storm flow. We'll then move up in scale from the hill slope to the headwater catchment, and then from headwater catchments to larger watersheds of, some hundreds of square kilometers. We won't go much bigger than that today. And yeah, the hope is to give you an idea of where I think things are now, and many of you are doing research in this area, and we'll look forward to discussion about these topics, some of the things that you might be doing with regards to hill slope hydrology. And again, stop me at any time if you have a comment or a question, but just like last lecture, we'll have, I think, 30 minutes or so for discussion at the end. Okay, so hill slope hydrology today, or certainly in the last few decades, following this period we talked about, which was the International Hydrological Decade, and then last class following that, talking about the use of isotope tracers and how that changed thinking. The work at the hill slope scale in recent years and decades has really been focused on the big question, and that is, how do hill slopes and headwater catchments or watersheds store and release water? What are the mechanisms for that storage and release? And here you're seeing in the photo some examples of hill slope scale experiments that I'll describe today. The upper 2 photographs are from the Mai catchment in New Zealand, and the lower is some sites in Oregon where we've worked, but I'll try and look at many others as well. You might know the name Brian McGlynn from the literature. This is Brian during his PhD work. And then let me try and activate my pointer here. There we go. And in the photograph here, driving the tractor is Marcus Weiler, who's now a professor at Freiburg University. This was during some of his postdoc work. So this is our question we're going to explore tonight, overarching question. How do these hill slopes store and release water? And the reason why this is important, as we talked about last class, is that because of the isotope data that's been coming in now in watersheds around the world, we realize that in many, if not most cases, there's just not enough old water in a discharge position to explain the old water volume in the storm hydrograph. Now, this isn't the case for all hydrographs, but for larger storms that activate the hill slopes, it's more than just the alluvial aquifer that's pumping old water into the stream. Water is coming off of hill slopes in different ways, and that's what we're trying to understand and explain. Hill slope engagement in the runoff process, and this is what's motivating it. Remember, we talked about Hewlett's conception of hill slope runoff. This was his famous variable source area concept. And remember that these lines, and this is a kind of an enlargement of the soil profile. And what you're seeing is this idea he had of lateral displacement, this translatory flow or displacement flow. So water from upslope continued downslope until it was so much flow was accumulating that water started to exfiltrate in the lower foot slopes and cause surface saturation in those areas. And he already was imagining, even though this was before isotope tracing had really started at the catchment scale, that a fraction of the runoff would be some of the actual raindrops that fell during the storm, that is some new rainfall, and the other fraction would be produced by a process of displacement. So he imagined this kind of piston-like flow downslope in this idealized diagram from his 1967 paper that we talked about 2 classes ago. Now, early on, we had the issue at the Mai catchment in New Zealand that we've referred to, and I gave a special lecture a couple of weeks on this topic that some of you might have listened to. And there, the question was, it's a site that has a lot of lateral preferential flow through soil pipes, and yet most of the water coming off of the hill slope or through the hill slope looks like water that existed in the hill slope prior to the event. And this is the conceptual model that I used in my PhD many years ago now to explain this. And this is really quite different to Hewlett's conception. It's not this lateral displacement like he showed in his diagram. It's actual preferential flow where water is moving to depth, new water, that is rainfall. It's mixing with a much larger volume of stored water in the soil profile. It's creating this zone of temporary saturation, maybe you might call it a perched water table or transient groundwater. And then once you had this condition of positive pore pressures, that's what would activate the lateral flow through soil pipes. And that water that would come out would not look like rain, it would look like water that existed in the hill slope prior to the event. But this is macropore flow of old water at this kind of plot scale on a hill slope. Now, what I want to do is move to larger hill slope segments. And let's look at this site. This is in Georgia in the southeast United States. Here's the hill slope surface. It's covering an area of about 20 meters by 40 meters. So 20 meters along the base of the slope, and you can see a trench excavated along the base of the slope indicated by that stippled line. And the surface topography is fairly planar, fairly smooth and planar. But now look at the subsurface topography. This is characterized by ground penetrating radar and also steel rods that we hammer into the soil until refusal. And what you see now is a highly variable soil depth. And this is, again, very different to Hewlett's conception, where his soil bedrock interface was very smooth and parallel. And this is showing that at most hill slopes, and certainly at this one, the subsurface topography is very variable. And as a result, the soil depth is highly variable in space as well. And what you're going to see is that water makes its way down to that soil bedrock interface, just like in the previous plot scale model I showed, and it feels that subsurface topography and then starts to exploit that flow path downslope towards the stream. So this is what we're going to look at now. And again, remember why we're doing this. We're trying to understand what is the mechanism to release old water from hill slopes to the stream during events. Because at least in this catchment and many of these steep wet catchments, there's just not enough old water near the stream to account for the old water volume in the storm hydrograph. This is looking at the trench. This is this kind of line, if I can show you my cursor. It's moving very slowly here tonight and not so predictably, but there's a kind of a line along the base of the hill slope. That's what this trench is. So this is excavated the full 20-meter width, and it's down to bedrock. And this varies, the soil depth is varying from about 25 centimeters to 2 meters. And all along this trench, we are collecting water and routing it through tipping buckets, and also analyzing that water for chemistry and isotope composition. we can also make predictions based on the surface and subsurface topography. Here's the same hill slope. Now I'm showing it in a way that uses something called the Topographic Index, where for each pixel, we determine the upslope contributing area, A, and we determine the local slope angle, beta. And you can kind of see that shown here. And the surface topography, this would be what we would expect the flow path to be. The darker the line is where the flow path would be expected. These are areas of high topographic index. So a high topographic index would mean a large upslope area, A, and a low beta, or slope angle. Whereas if we go up to the top of the slope, where the colors are more red or yellow, there we have a very small upslope contributing area, but a fairly large slope angle. So this is a measure of propensity for wetness, and it's widely used in Hillslope hydrology. But if we compare the surface topography to the subsurface topography, we see two very different patterns of what the flow pathways would be expected to be. And indeed, it's that subsurface topography that's explaining the distribution of flow paths down at that soil bedrock interface where all the action is happening. We're going to look at that in a minute now with some data. So here's what the hill slope looks like in photograph form. Down in the foreground along here, this is where the trench would be. So we're looking upslope from the trench. And these are many wells that are completed at the soil bedrock interface. And we can measure the spatial pattern of this perched water table, or so-called transient saturation. So here's the hill slope looking in plan view. Each dot is a well. And here we have a very small event, a small 5 millimeter rainfall event, and we have bits of saturation developing here at these two sites. Here's a bigger event, 9 millimeters, more patches of saturation down at the soil bedrock interface. Here's a bigger event still, 16 millimeters, almost 30 millimeters, still no connectedness from the upslope to the trench face down here. 50 millimeters of precipitation, and now at 59 millimeters we get connectivity from upslope to downslope. And here 61 millimeters, still more, even more connectivity. Now the importance of this is that if we look at total flow from the hill slope, this is the flow, the release of old water, you can see that it takes a precipitation event. Each dot represents a different rainfall runoff event. It takes an event of, 55 or 60 millimeters to activate the hill slope. And after that amount of precipitation here on the x-axis, now we get a very strong runoff response from the hill slope via subsurface storm flow. So this is a kind of a pattern that's a threshold, and that threshold is related to a spatial pattern that is the connectivity, not the conductivity, but the connectedness, the connectivity of these patches of saturation. And I'm calling this an example of filling and spilling that produces this. Here we're looking at it in just a different graphic. So again, small events, we get some patches of saturation down at that soil bedrock interface, bigger events, and only when we get to a certain amount of rainfall do we get connectedness of that saturation from across the slope, but to the base of the slope, where it then releases to the stream. If we look at this in cross section, again, the surface topography is fairly smooth. The subsurface topography is fairly irregular. This is a transect down the middle of the hill slope, and what you're seeing as we go from a small event to a big event, now we get this connectivity. So we're filling and spilling these depressions at the soil bedrock interface. And this is the mechanism for this threshold-like behavior of hill slope response to storm rainfall. Let's look at this at another site. We're back to New Zealand. Some of you have seen this hill slope. This is a very large trenched hill slope set up by Ross Woods at the University of Bristol now. But here's some flow data that we've measured. This is again flow on the y-axis versus total storm precipitation. Each dot is a different rainfall runoff event. And now look where the threshold is. It's only about 20 millimeters of precipitation that's necessary to turn on the hill slope and release old water from the hill slope. And we can compare that to maybe an area with much lower slope angle. This happens to be in South Carolina, where US elections are happening right now. This is on the coastal plain of South Carolina. You can see it's pretty flat, whereas this hill slope is probably about 40 degrees, 40 degrees. This hill slope is more like 4 degrees. So we've really relaxed the hill slope. Now look what happens. It takes almost 150 millimeters of rainfall to activate this hill slope. Almost like a tropical storm is necessary. Whereas here it's only 20 millimeters. And again, it's all happening down at that soil bedrock interface. So here's this, pardon me, soil surface. And here's this bumpy subsurface. In this case, this is an argillic horizon, kind of a clay, dense clay soil. Over here, the interface is a transition to an abrupt transition to a lithified conglomerate, which is the bedrock there. So again, you're going to have different types of materials. Could be saprolite, could be weathered or non-weathered rock, but these are textural contrasts that are responsible for this kind of filling and spilling, along with that bumpy subsurface. So here's again is ground penetrating radar inferred bumpiness to that subsurface topography that's kind of filling and spilling to create that threshold-like response. What does it look like? Here at MyMy, we've actually scraped away the soil, and now you can see the feet of one of my PhD students, Chris Graham, and we're pouring in some dye through a 2-meter wide trough, and you're seeing the very, these are like narrow ribbons of flow, and with the soil on top of this, this is still how I imagine lateral flow occurring, through these thin layers at that permeability contrast, and then the filling and spilling that then cascades down slope. This slope is fairly steep and not too irregular in the subsurface topography, and that's why I think the threshold is so low for activating this hill slope. Remember, this was only 20 millimeters necessary of rainfall to turn this hill slope on. So this is what I guess we're talking about in a kind of a cartoon-like way. This is from a book chapter by one of my former postdocs and his PhD student, showing at the hill slope we have these patches that might develop during a rain event, but we need a big enough rainfall or snowmelt input to result in connectivity of these patches to the downslope to turn on the hill slope. And then once we've done that, additional rainfall inputs just result in additional runoff at the hill slope scale. That's the main message here. And if we go to sites where I've been working over the last 30 years or so, these red dots are areas where we've done this kind of trenching. Over here on the right, the Panola site, the South Carolina site. These are some sites in California and Oregon and Alaska. Of course, MyMy here in New Zealand, and these are a couple of sites where we've collaborated with colleagues in Japan on Honshu Island. And for me, the runoff response is common across these mostly Pacific Rim sites, but even the sites in the Southeast United States. And that is, each of them have some form of filling and spilling with then loss along the flow path and deeper groundwater recharge all occurring simultaneously. But it's this interface between these two materials, again, whether it's soil and argillic horizon or subsoil, soil and rock, soil and saprolite, it's the conductivity contrast. And what we found with modeling studies, this is work by Louisa Hopp in 2009 in Journal of Hydrology, we found that that contrast needs to be at least 2 orders of magnitude to enable that ponding to occur and for lateral flow to occur at that textural interface. But I would say this is a surprising commonality of responses across quite diverse catchments. Now, you might be asking about preferential flow. And there has been work to kind of show how preferential flow aids and abets this kind of filling and spilling. This is a very nice paper by Henry Lynn's group. And sadly, Henry passed away about 1 year ago. But this is his group from Penn State University. And it's very lovely work they did at the Shale Hills experimental watershed, looking at how preferential flow through cracks and fissures and then even lateral preferential flow influences this kind of filling and spilling behavior. We've looked at this as well. This is some of the postdoc work of Marcus Weiler. This was a paper from 2007 in Water Resources Research, showing how soil pipes, here we've expressed them in a kind of a virtual way in a model, shows very network-like behavior at the Hillslope scale at MyMy as they interact with that filling and spilling in the lower soil profile. So I'm not saying that preferential flow doesn't occur, but I think this kind of filling and spilling is the overarching mechanism that can be aided by preferential flow if it's existing laterally at a particular site. All right, so we've talked about what I might call modern concepts of Hillslope hydrology, but we've really only focused on humid areas and areas that are dominated by subsurface storm flow, these steeper humid areas. What about overland flow? Well, again, this is my own biased viewpoint. So there hasn't been too much published on this, although I have a few papers out there, and I think much more work is needed. But we're going to look at overland flow and ask, how is it similar or different from this subsurface storm flow? And my hypothesis to you, or my proposal, I should say, is that it's all the same. That the filling and spilling we see at the soil bedrock interface is the same thing that we see in overland flow. Here's a photo from North Dakota. This is by Michael Chu, professor at North Dakota State University, and just showing how these kinds of puddles or saturated areas are forming on this agricultural field. Again, this is infiltration excess overland flow, where the rain intensity exceeds the soil infiltration capacity. But again, you have these patches of saturation that need to connect. And when they connect, then you turn on the whole hill slope. So my premise is that whether it's overland flow or subsurface storm flow, it's two sides of the same coin, we say. It's all effectively the same mechanism. So let's look at that. Here, again, this is, remember, infiltration capacity on the y-axis. This is the handwritten notes of Horton from the Horton boxes in the National Archives. This is the rain event here that we looked at a couple of lectures ago, and infiltration capacity, which decreases initially and then stabilizes, and the rain intensity is exceeding that infiltration capacity, and we get overland flow. Here, these are some data from Saskatchewan, which is just across the border from North Dakota. So again, a similar site. And here is work from a 5-hectare runoff plot assembled by authors here along the bottom. Again, this is flow and this is precipitation on the x-axis, just like you saw in those other examples. Each dot represents a different rainfall runoff event or snowmelt runoff event. And here we see, again, a threshold, in this case of about 60 millimeters or so of precipitation, and then the activation of the hill slope. Here it's quite scattered though. And why might that be? Well, in this kind of climate, we have both snowmelt and rainfall to contend with. And when the snowmelt occurs, it's often on frozen ground. And if the ground freezes wet or freezes dry, the nature of runoff production on that field is very, very different. If the soil freezes dry, then it still has a lot of infiltrability. If the soil freezes wet, then it's kind of like a parking lot and you get much, much overland flow. And I think this is what the reason why we have so much scatter for overland flow compared to the filling and spilling and conductivity response we see for subsurface storm flow. But I think it's still quite interesting that it's also fill, spill, loss along the flow path, and threshold connectivity. Here's an example of these plots. I just showed you data from one plot. Each of them, plot 1, 2, and 3, are 5 hectares. And there's a little device here, a V-notch weir, to record the flow from these hill slopes. This is what they look like in the winter, coming up towards the end of the winter from the 10th, 12th, 14, 16, 18 of March. And what you're seeing is snow melting on this frozen ground. And what we can do for these hill slopes is characterize the areas of filling and spilling. And this is what's shown here. The green is the fill, the fill is shown in kind of a reddy color. The green is the spill. And what you're seeing here is the upslope is in this part of the diagram. The downslope is here. So it's filling and spilling and behaving really rather similarly to the subsurface storm flow I was showing earlier. So fill and spill, I think, describes connectivity over frozen ground and over unfrozen ground based on the photos I was showing you earlier. So what I'm getting at is that if we have a hill slope, think of this irregular surface, whether it's the soil surface or a subsurface interface. This is bumpy by nature. Surfaces are irregular. They have microtopography, they have mesotopography, they have macrotopography. And this matters because this really relates or affects the patterns of connectivity. And when things finally get connected, that's when you have the threshold-like behavior from no flow to significant flow. And I'm showing this here in this kind of cartoon-like diagram. And then by the time we get to the catchment, all we then see is the rainfall runoff hydrograph. It's all smoothed out and smeared, as we might say. So this is the challenge. Often all we have to work with in a catchment is this, but if we go back some of these steps, this is what's ultimately, I think, generating this kind of response. So we're going to talk about how hill slopes link to larger scales here in a little bit as we talk about going up in scale. But my main message is, I think what we've learned in the last recent years is that we've gone from a paradigm of all runoff processes are different to one I'm advocating, which says that all runoff processes are the same. And they share the same kind of filling, spilling, loss along the flow path, connectivity behavior. And what I think this does, it opens up a lot of new modeling approaches. This is some work by a physicist named Daryl Jansen. A paper came out 6 years ago or so, and he's using directed percolation theory. So this is physics-free model, and you can see the hill slope scale where we've got rules for how water is percolating down slope. And what you're seeing is its ability to represent this threshold if we look at runoff on the y-axis versus rainfall. And I think thinking about the similarity of hill slope overland flow or subsurface storm flow really opens up new approaches. And this is, I think, an exciting area of research. But still, there's this loss along the flow path. And that's what I want to just spend a couple of minutes on. So we've talked about whether it's overland flow or subsurface storm flow. Remember, we talked about this in the first class. The runoff didn't come up and touch the rainfall. It only plateaued here. And the difference between the runoff and the rainfall is the loss into the soil profile. Or if this was subsurface storm flow, the loss into the deeper formation, into the saprolite, into the weathered rock. And it's this loss along the flow path I want to just spend a few minutes on before we continue. There's been some lovely work recently on this, but this is by a former postdoc of mine, Julian Klaus, and a colleague in Georgia named Rhett Jackson. And they've looked at this loss along the flow path by just comparing the conductivity contrast between the soil and the subsoil. So here's a kind of a cartoon showing you two very different downslope flow paths shown by that arrow there. One is very long and one is very short. And the very short one is if the impeding layer is more conductive, that is, there's a smaller contrast between the soil and the subsoil. And if you get a very long flow path, this would indicate a very large contrast between a permeable soil and a much less permeable subsoil. So we're going to look at this right now, and just to first cement in your head what we're talking about. So this was a rainstorm. I was hiking with my wife in Patagonia in southern Chile just before COVID hit, and we had to come quickly home to Canada. This was a small thunderstorm, and this was a flow path of water coming off of a concentrated area behind me. And when you see the water flow is going downslope, but it's infiltrating into the bed. And that distance of the downslope flow path, that's what I'm talking about here. How far did that flow path go before it sunk into what's below it? This is what we're talking about. So keep that in the back of your head if you can do that. And if you saw the MyMy lecture a few weeks ago, MyMy is one of the longest downslope travel distances of these 25 or 30 sites that were analyzed in this paper by Klaus and Jackson. So here on this y-axis here, this is a travel distance. This axis is the gradient ratio, so how steep the slope is. And this is that conductivity contrast between the soil and the subsoil. And what you're seeing here is that these travel distances in various hill slopes are varying from maybe some centimeters or maybe a few meters. Rarely are they going more than some tens of meters, except for these very steep catchments like MyMy that has a strong contrast between the soil and the subsoil. So I think this is an important feature, this loss along the flow path. This is what it might look like if you were to add some water on a hill slope. This is some lovely work by a group of colleagues in Italy. And what they're using is a time-lapse electrical tomography. So this is a geophysical technique. They're adding water along the hill slope here. And what they're doing is following how that water not only moves down slope, but also moves vertically into the subsoil after different number of hours, 0.8 hours, 4 hours, 19 hours. This is the end of the irrigation where they added the water, and then later on it drains and the soils dry out. Here is after several days. So loss along the flow path. There's even loss at MyMy on these steep slopes. Remember, we saw the hill slope threshold here was about 20 millimeters of precipitation. Here's one of my PhD students, Chris Gabrielli, and this is a 10-meter drill string that we're using a backpackable drill rig to now go deep into the subsurface, well, 10 meters into the subsurface. And we have 40 of these wells in this small hill slope and catchment. And what do we see? We see in this steep, wet area that about half of the groundwater that's recharged on these hill slopes is discharging down valley of this small hill slope and headwater catchment and subsidizing or adding to the flow of water in the larger watershed that it's a part of. And this is helped with some modeling work that we did in a paper that came out a couple of years ago. But it's, again, just showing you how even at a site like MyMy, which has the longest downslope travel distance, still there's water that goes into the lower formation, and this is contributing to groundwater recharge, and this water can take a long time to come out. Here we're looking at mean transit times of 90 years for this water to come out. And next lecture, we're going to talk about transit times and water ages. So we'll come back to this theme then. Okay, so far we've talked about the hill slope scale. What if we go up in scale? We think about how hill slopes interact with the catchments that they sit within. Well, the first thing I want to show you is that going back to old water and hydrograph separation, even at larger scales, old water is dominating. So here's discharge versus time. Here's two hydrographs for a so-called mesoscale catchment, a catchment on the order of 100 square kilometers in Germany. This is work led by Stefan Uhlenbrock. And it's showing the hydrograph separation between event and pre-event water. And you're seeing that a significant amount of the storm hydrograph here, in fact, most of the water is pre-event water. So this isn't just something we see at the hill slope or the headwater catchment scale. We see this even at large watersheds as well. In humid areas, at least, this domination of isotopically old water. So again, we have to understand these release mechanisms for the old water. So let's start with a catchment that's not too big. It's 10 hectares. And we're going to Oregon, and we're going to look at this catchment here, and we'll look at the hill slope here because we trenched this hill slope, and we can compare the trench flow at the hill slope to the 10 hectare watershed that's represented by this site. Here, the rainfall or precipitation is about 2,000 millimeters or so per year. So it's a wet site. It's forested. It's 50-year-old Douglas fir forest on this hill slope. And what we're going to do is do a hydrograph separation for that hill slope trench. Here's the rainfall. Here's the isotope composition of that rainfall. Here's the isotope composition of what's coming out the hill slope. And here's the hill slope hydrograph over this period of about 3 days. And you're seeing this response to the rainfall input, and look at the breakdown of event and pre-event water. Probably 80 or 90% of the water coming out of this hill slope is water that existed in the hill slope before the event. How does this compare to the catchment? Well, it's pretty similar. This is the same event, same input, but now here's the runoff isotope composition for 018. Here's the hydrograph separation. Again, we're using the simple two-component mixing model that we talked about last class. Remember, we're looking at the tracer concentration and solving that very simple two-component mass balance mixing model. And now you see that it's still dominated by pre-event water, but maybe a little more event water at the catchment scale. Question for you for the discussion period is why that might be. And I'd love to hear your thoughts on that when we have our discussion. Why we have a bit more event water at the catchment scale. But here I just want to show that as we go from the hill slope to the catchment scale, we still have this phenomenon of old water release to the stream. Now let's look a bit more at this site. This is an interesting catchment because the Riparian Zone, the area around the stream channel, was largely removed by a landslide. So it's a very nice catchment to work in because really there are hill slopes and then there's the stream, and there's not a riparian zone to complicate the geomorphology of this site. So here's a map of this small 10 hectare catchment. And what we're going to do now is look at some data from the hill slope and the catchment to understand this connection between hill slopes and the watershed that they are a part of. And again, this is a great site to start with because all there is in this catchment are hill slopes. There is no riparian zone, which is the other geomorphic position that characterizes headwater catchments. So here are some data covering a period of September, October, November, December, January, February, March. So several months here in this wet, very temperate place. Here's the rainfall. The rainfall, it's very dry through the summer months, and then the rainfall starts to increase, and then it's very, very wet. So what happens first? Well, first thing is a transition from the dry to the wet. And during the dry time, of course, the soil remains fairly stable in terms of its volumetric water content. That's what this middle panel is showing. So the top panel is the rainfall input. The middle panel is the soil moisture at these different depths down through the soil profile. And then the lower plot is the discharge, either from the hill slope in blue or the watershed in orange, that's at that, again, 10 hectare scale. So what do we see? We see before the event, the hill slope, on a per area basis, we're dividing by basin or upslope area to be able to compare directly the hill slope with its larger watershed. On a per area basis, the hill slope is yielding more water during low flow conditions than the catchment as a whole. Why might that be? Again, in the discussion, you might tell me what that might be. It happens to be, in this case, although there could be other reasons I'd like to hear your thoughts on, where that hill slope trench was and what it was next to in terms of maybe bedrock fractures that occur in basins like this. In fact, it was a seepage area. Anyway, during the transition, what happens? The hill slope starts to react, the catchment starts to react, and then after the system wets up here, now the hill slope and the catchment are one. They're behaving almost identically. The soil moisture has gone from a dry state to kind of a chronically wet state. And this is the relationship, I think, between, in steep wet areas, hill slopes and their catchments, when there's no riparian zone. So during the dry state and the transition state, the hill slope and the catchment are rather different in their behavior. But during the wet state, as I'm showing here with my cursor in the lower panel, boy, it's tough to tell them apart in terms of runoff on a per area basis. Now, what about a catchment that does have a riparian zone? Here we're back to the Mai hill slope. Remember, we saw this earlier. This is subsurface flow on the y-axis and total storm precipitation on the x-axis. Here we see that threshold. Remember, each dot is a different rainfall runoff event, and there's that roughly 20 millimeter rainfall threshold for activating the hill slope. But now let's look at the catchment that it's a part of. Here's discharge from the catchment. Remember, this catchment's small. It's only 3.8 hectares, very small. And here's precipitation. Now that threshold has kind of gone away. There's not the sharpness that you see here of the threshold. Here, any precipitation results in some discharge. Why is that? Think about that. Well, one of the reasons, of course, is that here we do have a riparian zone. So this is that area of an alluvial aquifer, if you like, a saturated area in communication with the stream in this wet site. So of course, any water falling on that wet area can immediately produce a little bit of discharge. But it takes still about 20 millimeters of rainfall to really activate the hill slope and increase the runoff response. Let me show you this a slightly different way that's maybe more intuitive. Here's runoff on the y-axis, and here are a couple of storms. And here, this first storm is a very small rain event. And if we look at the percent of hill slope and riparian runoff that makes up the total hydrograph, what we can see is that the riparian zone is the source of most of that runoff. But now the next event is much bigger, where it's activated the hill slope. It's beyond that 20 millimeter threshold. And what do we see? We see a roughly equal blend of hill slope water and riparian zone water. And for a bigger event still, maybe it would be mostly hill slope water with only a small finite fraction of riparian zone water. Now, if you look carefully, the green is the riparian zone, the red is the hill slope. You see that they're not quite responding at the same time. The green is leading the rising limb of the hydrograph, and the red is kind of dominating the falling limb of the hydrograph. And that's because if we look at these data yet another way, so same place, same data, if we look at hillslope versus catchment data, and we look at it in kind of a hysteretic pattern, and the rising limb is shown by the dark circles, and the falling limb of the hydrograph is shown by the open circles, the relationship between the hill slope and the runoff at the catchment scale is anti-clockwise hysteretic. Whereas the riparian zone is the opposite. It's clockwise hysteretic. That means that on the rising limb, it's being dominated by the riparian zone, and on the falling limb, it's being dominated by the hill slope, right? Because the hill slope has to turn on after a while, and then it dominates that latter part of the hydrograph. So this is really a function of hill slope riparian zone sequencing that happens at the headwater catchment scale. So we're thinking now about how hill slopes interact with their catchments. They interact through this riparian zone that's so important for runoff generation. We can go larger still. This is very nice data from Kelsey Jensko, part of his PhD that he did with Brian McGlynn. This is a paper they had in 2009. And what they did in this watershed, this is going even bigger now, they've mapped along the stream section when the hill slope connects to the riparian zone in the stream. So they've put wells in along the stream zone, along the base of these hill slopes, and they created this lovely plot between the percent of the year that the hill slope was connected to the stream and the upslope accumulated area for where their wells were throughout this set of catchments. So these are all sub-watersheds here at this site in Montana in the United States where they worked. So let's just look at another way of looking at it. This is a way that you can visualize then the connectedness, the connectivity of hill slopes to the stream channel via this via the riparian zone. This is very nice work that they did. The last example I want to give in terms of hill slope catchment and then larger catchment interaction is from a site in California where we worked. And it really gets at the question of how much water can a watershed store? How much can it fill before it starts to spill? And now we're talking at the scale of 100 square kilometers. So we're going to look at this catchment here. This is a 100 square kilometer catchment, and within it are a whole series of smaller watersheds, 10 of them, that we gauged over a period of several years. This is a lot like the site in Oregon, which is just north of California, in that it has a long dry season and then a kind of a progressive wet season. So here's the start of the wet season in November. We've just had a few months of almost no rainfall, and then we get rain event after rain event, this very, very wet sequence over these 4 or 5 months, and the stream starts to turn on at the 100 square kilometer scale. And what we're going to do is a very simple calculation of the change in storage based on rainfall minus runoff minus evapotranspiration that we calculate. And what we're going to ask is how much do these systems fill before they spill? So we're going to start the calculation here at the beginning of the wet season, around November 6th. And we're going to do this very simple calculation measuring the rainfall minus the runoff minus the evaporation and calculate this DV, change in storage. Let's look at it for this is DV now on the y-axis, and this is that same x-axis period. Remember the start of the rainy season in early November, and then the catchments filling and then spilling as they plateau here. These are the small catchments on the order of 3 to 6 square kilometers. So these are just catchment numbers, and the numbers in parentheses are the actual watershed area. So this one's 3 kilometers, square kilometers, 5 square kilometers. And what you see is they all start to fill, but then they start to spill at different levels. And the final storage, how much water the watershed can store, it's varying from about 500 millimeters of rainfall to this particular catchment that can store about 200 millimeters of rainfall. And this is same behavior for the larger watersheds. Here's the whole watershed, 112 square kilometers. Here are some others. This is a 50 square kilometer watershed within it, 57, 20. And again, you're seeing values that are ranging from about 200 millimeters of precipitation up to about 450. So what is this saying? If we go back to this relationship between discharge and change in storage, what we see is that the catchments are, as we go through an event, filling, and then spilling, where we get this almost vertical-like change in discharge once we exceed this threshold, this filling of the watershed. We're not able to say what the kind of the granularity of the filling and spilling at the Hillslope scale is, right? We're up at the 3 to 6 square kilometer basin scale, but these catchments are almost themselves acting like reservoirs that are filling and spilling. This one's a little more complex. It gets to be about 300 or so millimeters of storage, and then it starts to spill, and the process here is a little more complex than the other watershed. But both of these examples, and all of the examples, whether it's this so-called mesoscale, a headwater catchment scale, or the top panel, the Hillslope scale, I think are all versions of filling and spilling. And really the question is, in terms of how you might diagnose this, it's first identifying the scale that you're interested in, and then trying to understand what is filling and spilling at that scale. So we don't need to resolve this kind of Hillslope scale behavior if our interests are at the scale of 100 square kilometers. And similarly, even at 100 square kilometers, we're not really thinking about Hillslope Riparian Zone connections. We're thinking about perhaps sub-watersheds on the scale of a square kilometer or two, and how they are filling and spilling and contributing to runoff that we see at that scale. I'll end with an animation. This is as fancy as I get, and this was with assistance of a former postdoc, Takasayama, who did some work along these lines. But think of this storage-discharge relationship, whether it's filling storage, remember those patches of saturation at the Hillslope scale, or if it's filling storage at the headwater catchment scale, or filling storage at these large mesoscale. We get this relationship where along this part here that you see right now, we get big changes in storage with little change in discharge. And then when it wets up, we get big change in discharge with a little change in storage. This would be a catchment like the one in Oregon I showed, the H.J. Andrews. It has a dry season here, it has a wet season, and it has very different behavior, whether it's dry or wet season. The Mai catchment in New Zealand, which is what I'm showing here, is really spilling most of the time. Remember, it only takes about 20 millimeters of rainfall to activate this hill slope. It never gets down into this area here. It's always in this kind of vertical zone, very high runoff response. And then the site in Georgia that I talked about, the Panola watershed, it's the opposite. It stays down in that kind of horizontal piece where it's always filling storage. It's not spilling very often. You need about 60 millimeters of precipitation. That doesn't happen too often. And what we're going to talk about next class is how discharge and storage ultimately define the age of the water, because the age of the water is simply storage divided by discharge. So this catchment, as you'll see in the next and final class, has water forming stream flow on the order of a few months old. This watershed, the water in the stream, the age of that water is on the order of a few years old. And here, the base flow in this stream channel is on the order of a few decades old. Storage divided by discharge. So we're going to think about this as it relates next time to things like the age of the water, the transit time, and how we can incorporate these ideas of storage and discharge into our modern concepts of runoff behavior at the hillslope, catchment, and mesoscale. Okay, so let me try to wrap up. What we talked about today is these so-called modern concepts of hillslope runoff, and I've tried to tell you a little bit about this fill and spill behavior and how overland flow and subsurface storm flow, I think at the hillslope scale, are effectively the same. And when we go beyond the hillslope into headwater catchments, of course, it's really that ratio of the hillslope and the riparian zone, and how event size determines which one is dominant over the other for releasing this old water into the stream channel. And then for larger watersheds still, this concept of, again, filling and spilling, but at the kind of larger scale. And again, back to the hillslope scale, I think this balance of filling and spilling has a lot to do with the slope angle. It has a lot to do with the permeability contrast between the soil and the subsoil. And what we see is that it begins to go from perhaps a fill-dominated landscape to a spill-dominated landscape as we go steeper, as we get greater contrast between soil and subsoil, as we have longer downslope travel distances. And I think this kind of ratio, or thinking of the filling to spilling ratio, can be a helpful way to come at runoff processes and whittle down these process details, as Siva Palin encouraged us to do in the first lecture, to something that we can communicate to a model structure, for instance, at these larger scales. So we talked about this, and one thing I guess I'm kind of coming to the idea is that really runoff is at the scale of the beholder. And I think that there's a lot of hope for a unified theory of fill and spill and threshold response, where this is a highly conceptual diagram, but at these small scales, you can have filling and spilling, and this filling and spilling kind of cascades to larger and larger scales. But really, it's the scale that you're interested in is really determining where you're looking for this kind of fill and spill behavior. This is a paper that's in review now in Water Resources Research that I hope I can share with you in the coming weeks or months. And maybe the last thing I'll mention as a segue to next class is I think our challenge is really getting at these modes of connectivity. Again, it could be overland flow, could be subsurface storm flow, but really our challenge is to understand this kind of connectedness. And this was a lovely review paper written by Teresa Bloom and Ilya van Meerveld. And then as we go up in scale, how the hillslope to stream network connectedness pattern occurs. These are, I think, our challenges in field hydrology and in catchment hydrology. And the tools that we use to do this will be these isotope tracing techniques. It will be geophysics, it'll be trenching, it'll be tracer additions. And these are, I think, the ways that we're going to understand better how hillslopes connect to the streams that drain them. And I'll leave it there and maybe leave this diagram up because this is how we'll hand off to the next lecture. But I think a lot of it comes down to this, and that is this quote by Keith Bevan in a lovely paper in Hess in 2006. The boundary conditions are the science. I think this is true for what I've talked about today. If the boundary condition is the surface topography for overland flow, it's really the bumpiness of that surface topography in terms of what controls the filling and spilling. If it's the boundary condition is the soil bedrock interface, that too, that irregularity really dictates the nature of the kind of the filling and spilling and these idea of connectivity that we've talked about a lot today. So I'm going to leave it there, and I'll open up the screen, and hopefully there might be some questions in our final half hour or so that we have.
Yeah, we can ask some questions.
Yeah.
Just I remember you have a graph, and you told the hill slope and the catchment scale, or the maybe the hill slope can generate more runoff per maybe just per square meter or some. You give the compare the
right
curve, yeah.
Right. Yeah, that was during low flow, and that's because the hill slope trench was on a groundwater seepage zone, so it's kind of a unusual place in that the groundwater seepage zone was sustaining stream flow between events.
Yeah,
I'll just draw a picture really quickly, and then hopefully I can show it to you. So what we and other groups had found, if this is the watershed, I'm not sure you can see it. So here's the watershed, and here's the stream network. These dots here are groundwater springs. So these are fractures in the bedrock. The bedrock here was breccia, and these are andesitic, or not andesitic, but dikes that run through the breccia. And this is what is controlling the low flow during the summer when it's not raining. So it's deep groundwater coming through springs. And the trench was placed, the trench that was excavated was put on top of one of these springs. So that means that when it wasn't raining, the trench flow was biased to the flow from the spring. And then when it started raining, the flow from the spring was very small compared to the amount of water flowing as subsurface storm flow. Yeah. So I think that's characteristic of a lot of watersheds in humid areas. Under dry conditions, we see deeper, older bedrock groundwater. And under wetter conditions, we're activating shallower flow paths, younger water. And it's that blend of water that we'll talk about next week when we talk about the mean transit time of waters getting into stream channels.
Yeah. So just you when you did the research on the hill slope and the catchment scales, you also measured the on-ground water table.
In some systems, yes, and some we weren't able to, but we try to do that now all the time, because understanding that connection is important, because much of the water that is infiltrating the hill slope doesn't go laterally, it continues to go deeper to recharge groundwater. And I think that's another new area for hill slope hydrologists, is to really understand as well groundwater recharge processes.
Yeah.
The water that doesn't,
So I found maybe you mainly focus on the storm event. Yeah. Just each storms, each rainfall, we made the overland flow and the subsurface flow. Maybe the on-ground water is very stable in the humid area.
Groundwater. Yeah, I think the groundwater is stable, both isotopically and in terms of its water level.
Yeah.
But how it's recharged is not stable. I think there are certain special conditions that can recharge groundwater at times of the year, or under certain hill slope conditions that are very different to other times of the year. So for instance, in North America, often it's the period during snowmelt, which is the most important time for groundwater recharge, because there's not competition for that snowmelt water by vegetation, and it's a time of wet antecedent conditions, and as a result, our groundwater is often isotopically lighter than the mean annual precipitation, because it's biased to cold season recharge. And I think that occurs in many mid-latitude areas, for instance.
Yeah.
Yeah.
I also have another question. Just I'm interested in your research on the catchment, different maybe plots on the soil moisture. I found the many measurement plots in the how did you design the where we should measure the soil moisture in the catchment?
Yeah. The well was really measuring the temporary water table response.
I mean the soil moisture, just for the
soil moisture we measured with TDR, domain reflex.
How to design where we should measure the soil moisture? I found the different areas you measure the soil moisture and separate different soil layers.
Well, I guess it depends on. Often it's practical considerations that define that. It's how many TDR probes do you have? What is your question you're asking of those data? We've made kind of Hillslope grid pattern installations before, where we've not known anything about the soil moisture, and we often find a grid is a way to first understand the Hillslope response in terms of soil moisture.
Yeah.
But it could be a transect. There could be, again, I think it depends on the question. For my work, I'm more interested in these spatial patterns, because we've found that the patterns really are what is describing the connectedness of the Hillslope.
Yeah.
And turning it on.
I just found your research on the connectivity. From the upslope to downslope and the whole slope. So we can use the soil moisture data to find the connectivity.
Well, yes and no. I think my main message from the subsurface storm flow work today is that temporary saturation is the precondition for lateral flow. If you don't get saturation at an interface, and if it doesn't connect to the whole slope, then you don't activate the hill slope. So therefore, soil moisture may not be the best measurement. Water table depth and its distribution is maybe a better measure. And that's where we used a maximum rise well. And a maximum rise well is a very simple device. I'll try and draw it here.
Yeah, I'm interested in,
And so we have a, sorry, I'm drawing quickly. And we have a, okay. So here's my my terrible diagram. This is here's the soil surface, and here's the soil bedrock interface. And this is the well that we've drilled, we've augered, and inside the well we have a plastic tube. And in the plastic tube is a cork, a piece of either a cork or a piece of styrofoam. And what happens? It rains and water infiltrates, and then the water forms a water table here. And what it does is it pushes up the cork, because the cork is able to float. And now the cork is here.
Okay.
So it pushes up the cork, and then the water table falls down, and the cork is stuck here.
Yeah, can record the float and down and up. Yeah.
But it only goes up, it doesn't go down. Because it gets pushed, and it records the maximum rise. So then what you do is you come along after the event, you take this tube out of the ground and you record what that maximum rise was. And that tells you whether A, you saw any temporary saturation, and B, how much there was. So this is a very simple but effective technique to map that temporary saturation at the hill slope scale. So it's a very simple but useful technique for patterns.
Yeah. Thank you.
Yeah. Other questions from students?
Hi, Jeff.
Hi.
Thank you. Really exciting speech. I think maybe the filling and spinning can not only occur on the spatial scale, and also can occur in the temporal scale. Example, in the Tibet Plateau, only in the summer can show that the strong filling process, and all the other periods there was very little rainfall and precipitation. So it shows that the non-time release and non-time spinning. And I think maybe spinning can occur in two cases. The first is over exceeded infiltration, and the second is the infiltration like the non-one knows like this. So I think maybe spinning can not only occur on the spatial scale, but also can occur in the temporal scale.
Yeah. I'm not sure I fully understand what you're saying. I guess, do you mean filling and spilling can occur in the temporal scale because runoff itself is threshold-like? Or are you referring to maybe thawing of frozen soils that you have that are happening at different times through the seasons? I'm not quite sure what you mean.
In the Tibet Plateau,
yeah,
most rain precipitation is occurring in the summer.
In the summer, yeah.
Yes. In the other period, there was very little precipitation.
Yeah.
But the base flow is almost occurring. So in this time, I think it also the spinning process. In the other period, it is the spinning process occurring in the temporal scale. Temporal scale.
Interesting. And is that because of thaw or what? How is the spilling happening outside of summer? What's causing that spilling, if that's what you're saying?
Two cases. When the rainfall occurred, not all rainfall was spinning as a subsurface flow to the river, and another is stored in the catchment. Is stored in the catchment. So this part of the rainfall is slowly released in the other period.
Okay. Yeah.
So that is why it is the water tower of the ash. I think maybe it can plan in the time scale.
Yeah, it's interesting. So how is that sustaining of flow different to just groundwater discharge and base flow? Is that what you're referring to, or is it something different to that you're describing?
I'm sorry, cannot quite understand.
Okay. I guess it goes to the age-old question of why do streams flow when it's not raining?
Yes.
This is a question that people have asked since the ancient Greeks. For 2,000 years, people have asked this question. And Hewlett's work in Coweta in the United States, he wrote some papers saying that base flow, meaning flow in the stream when it's not raining, is due to unsaturated drainage from the hill slopes between events.
Yes.
Since then, I think most studies have shown that's not what drives base flow. Base flow is really groundwater discharge. It's often deeper flow coming into the stream linked to groundwater and phreatic conditions in the system. So I guess outside of your summer period in the Tibetan Plateau, what do you think is the source of the base flow? Do you think that's groundwater discharge? Is that what you're saying?
Yes, mostly. Yeah, or some deep subsurface flow.
Or deep subsurface flow. Yeah. Interesting.
But the difference is in the Tibetan Plateau. When it is in the winter, the water will be frozen.
Mm-hmm.
So until in the next spring, it will be thawed and slowly released.
Mm-hmm. Okay. Yeah, and even the stream is not flowing in the winter; it's fully frozen as well. The stream flow.
It have as the stream flow in the winter.
Okay. Interesting. Well, you and I can talk more about that when we meet. I find that very interesting, and I'll enjoy learning more about that.
Thank you. I have a lot of questions.
Yeah.
So you detect the subsurface topographic with a head O and the GPR. So the question is, I wonder, maybe the high density of the head O will destroy the surface topographic. And the second, is, in the catchment, they have vegetations like the forest of the shrubs. So it will make problem to use GPR or radar, nothing else.
Yeah, it's difficult on forested hill slopes. It can still be done, but you're right. In many ways, it's easier to just use a steel rod. The Japanese have a device that they use a lot called the knocking pole penetrometer. It's a cone penetrometer like a soil mechanics researcher would use, and basically you drop a 5 kilogram weight and it pushes the rod deeper and deeper into the soil, and you record the resistance to penetration. So it gives you kind of a vertical profile of resistance to penetration, which is kind of a surrogate for conductivity. And then you do that until refusal, and that tells you the total soil depth. And we use that tool a lot, and it's much easier on these vegetated slopes, whereas you say it's difficult to use a ground penetrating radar sled or other geophysical devices.
Yes. Mm-hmm. I have another question.
Yeah.
In the Tibetan Plateau, the Hillslope threshold behaviors show dynamic characteristics across the seasons. You said in the other catchment, the precipitation threshold is maybe 115 millimeters or 50 millimeters, but in the plateau, it shows dynamic characteristics across seasons.
Interesting.
In the spring, the threshold is very neat, very small. For the threshold Nile depth is very shallow.
Yeah.
But when it is rounded down and the threshold bigger and bigger.
Yeah. There have been a couple of papers that have looked at that in some watersheds in the United States. There's a paper by Detty and McGuire, I think around, pardon me, the mid-2000s. I can get you the reference if you like. And they looked at the threshold, but they combined the threshold with antecedent precipitation index. And they found, like you're describing, the antecedent precipitation index was an extra very important measure for defining the threshold response. Because like you, the threshold was variable through the year, and it was affected by the wetness before the event.
Yes, wetness and the frozen ground.
Yes, and I think that's where you've got really interesting data with your frozen ground, because very few studies have looked at the things I'm talking about in the context of frozen ground, and I think that's going to be really interesting with your presentation of work showing this kind of behavior. For much of the world has this kind of, you know, frozen, or a lot of our key water towers, as you say, has this frozen ground aspect to it. So that'll be exciting when you publish that research.
Thank you, Jeff. Really excited. Really excited. Thank you.
Thank you. Other questions?
Hi, Professor. Hi, Professor Jeff.
Hi.
This is Muzi.
Hi, good to see you.
Yeah, good to see you again.
Yeah.
Thanks for your excellent presentation.
Oh, thanks.
My question goes with one of your slides, which you compared the my curve into another two curve about the store. Can we go to that slide?
Oh, sure. Yeah.
Thank you.
Yeah. Almost there. Yes. Okay. Here we go. This one, do you see it? Oops, not that one. Sorry. This one.
Sorry.
Yeah, this one?
Yes, that one. Yeah. So my question goes that because I remembered you mentioned that the my atmosphere is the environmental humidity is very high.
Yeah.
So my question goes that the curve rate is dominated by the environmental humidity, or it is dominated by the slope gradients? Because because as my imagine, just like we can take the shower head for example. If the vertical gradient, the shower head, the fill and the spill process will goes very quick. Otherwise, it will come slow. But just as you mentioned that if the environmental humidity is very high, and then the storage in the soil is very high too. So I just would like to ask, I just would like to wonder which is the dominant for that curve.
Yeah, no, it's a very good question. Very perceptive question. So I think it also relates, and maybe mostly relates in this case, to the fact that at Mai there's very little seasonality, meaning it's always wet. It rains at Mai every other day. So of the year, about 150 days have rainfall. So it never drains. It's just chronically wet. So because it's wet, just like Hu's last question about antecedent wetness, it has very high antecedent wetness all the time. So you never are able to really get down into this area, if you can see my cursor. Why? Because the rain never turns off long enough to see that. Whereas this site, it's a different type of climate. It's what we call a Mediterranean climate, which has a long dry summer where it doesn't rain at all, and the whole system can drain. And then it has a very long wet winter, and it stays up here. But over the whole year, it's traversing all of this curve. Whereas this site, it is kind of always water stressed by comparison, because this site is maybe 2,500 millimeters of rain. This also has about 2,000 millimeters of rain, but it's only falling in 6 months. The other time of the year is dry. And then here you have maybe 1,000 millimeters of rain, but it's in a very subtropical area with a lot of evapotranspiration, so that it's always kind of a bit water stressed. And I think you're pointing at some important things that we'll talk about in the next class, and that is how to bring in climate, how to bring in seasonality, how to bring in whether the rainfall is falling in the summer or the winter. Sort of, is the rain, is the hydrology in phase or out of phase with the ecology? So imagine Switzerland. It's a humid, warm place in the summer, and most of the precipitation in Switzerland falls in the summer. In Oregon, here, most of the precipitation doesn't fall in the summer, it falls in the winter and runs off. So the eco-hydrology of these two systems is very, very different. And I think your question's getting at that interesting interaction between the hydrology and the ecology. And this is actually something we'll talk more about next class, but that's a good question, Muzi.
Thanks for your answer, and looking forward for the next session very much.
Okay.
Actually, it is very interesting because it's not a simple like linear equation into unknowns. It's so many complicated information, and yeah, you need to identify that.
Yeah. I mean, this is nature, and this is the very difficult thing in hydrology. You pick up a textbook like the textbooks on my shelf here, and you look at, I don't know, a book like Principles of Hydrology, and what do they say? They say, well, if you're interested in soil water movement, you use Darcy's law and Richard's equation. If you're interested in stream flow, you use Saint-Venant's equation or a kinematic wave routing. And it's all taught as if it's very easy and straightforward and we know what's happening. But I would say in all these books, we don't know what's happening. We don't understand how water infiltrates and moves down slope. And that's, I think, resulted in the fact that we have these very, very simple models that bear very little resemblance to reality. We go into Professor Pan's site in the Lus Plateau, or we go to some of my sites, or we go to Guang Ronghu's site in the Tibetan Plateau, and we dig a hole and we look at our textbooks and think, oh no, how is this ever going to work? This doesn't look anything like you know, the equations we're given in our introductory textbooks. And I think the future of hydrology is somehow recognizing that complexity and realizing that we have to finally deal with it. Because if we don't, we're not going to be able to make predictions for climate change impacts. We're not going to be able to make process-based predictions for land use change impacts, because as you're pointing out, these interactions are very nonlinear and very complex and very exciting. And this is the science of hydrology, I think, that we're hoping to you know, promote to students in the class, that hopefully will go on and learn many things. Yeah, but good question. Any any final questions before we wrap up tonight? Anyone else want to ask a question?
Yeah, maybe
Yeah.
I have a question.
Sure.
Yeah,
sure.
yeah. Just in recent days, I also do some research on the soil moisture, soil water movement from the hillslope, on the hillslope. I I'm imagine that maybe some water infilled into the soil up on the upslope, maybe will move to the hill slope, but I cannot calculate and estimate how much water can be moved into the downslope, and and how many distance from the upslope to downslope. Can you give some suggestions if I do some research on this?
Yeah.
In the lost potato, just maybe the soil moisture is very high soil layer and even and like this. Maybe I think maybe in the deep slope, in the deep soil layer, maybe some on the top soil maybe have a low density. In the deep soil layer maybe has a higher soil density. Maybe has some difference. From the up to
Well, I guess to get the direction of soil water flow in the unsaturated zone, you need tensiometers to measure matrix potential. And if you have matrix potential, and then you can measure the depth of the ceramic cup of the tensiometer, you can calculate the total potential. And then when you have many tensiometers where you now have a map of total potential, you can draw the flow lines at right angles to the total potential and get the direction of flow. And then, of course, I guess to get at how far it might travel, you need to know the unsaturated hydraulic conductivity. And that's another difficult thing, because the hydraulic conductivity, as you know, is so affected by water content and matrix potential. So this kind of gets back to the answer of Muzi's question. So many complex nonlinearities, and that's just in the matrix. That doesn't include any preferential flow that could occur during an intense rainfall event. So I guess what we usually resort to is a model in this case to help us. So in North America, Europe, we might use Hydrus, 1D, Darcy-Richards solver. Now there's Hydrus 2D, and we've used Hydrus 3D. And that can be a way to use some numerical simulations to get at an answer to your question. And then I guess it's that dialogue between your field measurements and what the model suggests, where you try to understand how realistic those estimates are for your site. But these are, in some ways they're such simple questions, and yet in other ways they're so difficult to answer, because all these things are interrelated in nonlinear ways with feedbacks and thresholds and hysteresis. These are all examples of nonlinearities in our hydrologic systems that make these calculations quite difficult. So I'm also focused on the vegetation, the impact of the vegetation on the soil moisture movement. And that's great, because that'll be the topic we describe next class. We're going to look at vegetation and what goes on between events. So going back to Hu's question of when it's not raining in his site in the Tibetan Plateau, it's raining in the summer. What happens when it's not raining, and how does the vegetation remove that water? And that's maybe something we'll talk about in our next and final class.
Thank you.
Good. Well, good
Yeah.
seeing everybody again.
Yeah, thank you. Maybe we can. Thank you, Jeff.
I'm going back now to watch the American election and see what happens.
Okay. Vote. Yeah,
Bye,
yeah. Thank you.
All right. Thanks. Thanks for the great questions tonight.
Thank you.
See you.
See you.
Bye.
See you.
Bye.
Bye.